All right, everyone, we'll go ahead and get started. Thank you so much for joining us today. My name is Danica. I am with 3C Ren in the County of San Luis Obispo, and welcome to our last webinar of the year. It's Understanding Heat Pump, HVAC, and Water Heating with our expert, Russ Gang with Coded Energy. And before I pass things off to Russ, I just have a few logistical slides to go over. A few quick Zoom reminders before we get started. Please make sure you're on mute throughout the duration of the training. And we do highly encourage questions. And if you have them, feel free to put them in the chat, or you can raise your hand and we can unmute you. And this session is being recorded and will be shared with you along with the slides in the next few days. And that's been asked in the chat. So just a heads up that it will be on your inbox. And next slide, please. And if you are new to 3C REN, this is just a little bit about who we are. We are the Tri-County Regional Energy Network, and we're a collaborative partnership between San Luis Obispo, Santa Barbara, and Ventura counties. We are funded by ratepayer dollars collected through the public goods charge, and the benefit of that is that there's no cost to those we serve, and we are able to bring those dollars back into our region. Next slide, please. And 3C Rent currently offers three services. We have incentives, trainings, and technical assistance. This training today is brought to you by our Energy Code Connect program. If you're interested in learning more about our other programs, feel free to visit our website at 3c-ren.org. And with that, I'll pass things off to Russ to get our course started.
Thanks, Danica. How's this sound? Everything sound okay?
Yes.
Great. Well, thank you very much. It's my pleasure to be here today. And we appreciate you all taking time out of your day to come and get this important information. This class is actually a combination of two classes. So it's going to start off talking about space heating, heat pumps for space heating, and then at the end we'll talk about space heating or water heating, heat pumps for water heating. So as you can kind of tell from this picture, heat pumps have been around for a long time. They're fairly new to the United States, but they've been around in Asia and Europe and Central and South America for a long, long time. The very first time I saw a heat pump was when my family went to Mexico. The condo we stayed at had a heat pump, and I had never seen one before. This was, gosh, 25 years ago, maybe. And well, here they are. They're everywhere now. They're quite ubiquitous to everything. And so that's what we're going to talk about today. The first part is talking about space heating and cooling. Okay. So the agenda, we're going to talk about, we'll do an introduction, but then we're going to have some terminology. I think it's really important to sort of lay the foundation of what we're talking about so we're all speaking the same language. And then we're going to talk about some really super basic thermodynamics. I know thermodynamics is a great cure for insomnia. It will put people to sleep immediately. So I'll try to keep it short and sweet so that we can explain the refrigeration cycle. I think it's really super important that in order to appreciate heat pumps and what they do is that you at least have a really basic understanding of what the refrigeration cycle is. Okay. Then we're going to talk about advantages of heat pumps for space heating and some disadvantages. And we'll talk about the different types of heat pumps for space heating. And then we'll talk about how to size heat pumps. That's super important is properly sizing heat pumps. And then we'll kick into the slides for the water heating portion of the class. All right. So my name is Russ King. I'm a mechanical engineer. I'm the CEO of a company called Coded Energy Inc. We're the developers of a software called Quick Model 3D. We also manage a website called DIYLoadCalcs.com. I do lots of training. This class actually was originally done for Bayren and then Sonoma County and then Marin County. And today I am literally wearing my 3C Ren hat. So happy to be here and present this information to you. I've been doing this for a long time, 35 years. Most of my career has been doing HVAC design, but I've done a lot with energy efficiency consulting and testing of homes and all that good stuff, and training, of course. There's my email. Feel free to contact me if you have any questions, russ@coded.energy. I have an HVAC blog where I talk a lot about HVAC topics, russellking.me. And then I also wrote a textbook that's used in some community colleges and trade schools. It's a very introductory textbook called HVAC 1.0 Introduction to Residential HVAC Systems. So, with that, let's talk about heat pumps. All right. So, to really understand heat pumps, you must first understand a little bit about why and how we heat and cool our homes. All right. So the main reason is for comfort, to keep a certain temperature. The house is a bubble that we live in to separate us from the outdoors, right? We are very spoiled. We like to live at a certain temperature and humidity and things like that. So we have this self-contained little bubble that we live in. And that bubble, we like to maintain a constant temperature. And so that's the goal of a heating and cooling system, is to maintain a constant temperature. But we want to do that as efficiently as possible. So the excessive use of energy and heating and cooling is a big part of all the energy that we use, has a lot of negative impacts. And so we want to accomplish that goal of maintaining a constant temperature as efficiently as possible. And not just for environmental impacts, but because it's cheaper if we can do it more efficiently as well. So cost effectiveness is a big issue when we start talking about energy efficiency and things like that. So we'll talk about that. So HVAC stands for heating, ventilation, and air conditioning. The main goal of an HVAC system is to maintain a constant temperature inside the house. Houses lose heat in the wintertime and gain heat in the summertime. And so we have to offset that. We have to offset the heat that's being lost in order to keep it warm inside the house. And we have to offset the heat that's coming in from the outside in order to keep the house cool in the summertime. So to maintain a constant temperature in the winter, the heater has to replace BTUs. That's thermal energy. Okay. So the house is losing heat, the heater replaces those. And in the winter, the opposite is true. The house is gaining heat. Heat is coming into the house in the summertime. And so what the air conditioner does is actually remove those BTUs. So it's important to consider and think of cooling as removing heat. All right. We're not adding coldness to a house. We're actually removing heat from the house. So the terminology, first of all, what the heck is a BTU? All right. A British thermal unit. It's how we measure heat. Okay. So it's a unit of heat, and it's approximately equal to the amount of heat that's stored in a wooden kitchen match. So if you take a match and you strike it and you let it burn all the way down, you've just released 1 BTU of heat into the air. All right. But when we talk about BTUs, we talk about BTUs moving from one place to another. Either we're putting BTUs in, or our house is gaining BTUs naturally and things like that. And so when we talk about BTUs, we typically express that as a rate of BTU movement, or BTUs per hour. Okay. So you'll see it, and it's written in a bunch of weird ways that don't make any sense. But one of the more common ways to write it is BTUH. That means BTUs per hour that's moving or being moved from one place to another. Okay. All right. So because a BTU is approximately equal to a wooden match, this little symbol, the flying kitchen match, is going to represent BTUs in the following diagrams. Okay. Another interesting term that we hear a lot is tons. How many tons is your air conditioner? How many tons is your heat pump? All right. Well, it has nothing to do with the weight of the equipment. It's an old term that goes way back when we used to, before mechanical cooling and refrigeration, we used to buy ice by the ton. So a ton of ice had a certain amount of cooling capacity. It had the ability to cool things. And so a ton of ice, turns out, has a cooling capacity of about 12,000 BTUs per hour. And so when we say an air conditioner is a 2-ton air conditioner, it's 2 times 12,000, or about 24,000 BTUs per hour of cooling capacity. Now that's nominal capacity. All right. So when air conditioners and heat pumps, they test those. When they rate them for their size and they name them a 2-ton air conditioner or a 3-ton air conditioner or heat pump, we call that the nominal capacity. It's the capacity that they just name it. All right. But that happens in a very controlled laboratory setting. When you install that air conditioner in an actual location, in an actual house under exact certain conditions, we call that the installed capacity or sometimes the design capacity. Okay. And it can be a little different. So the actual capacity of an air conditioner or a heat pump depends on the conditions under which it's operating. All right. So we might call it a 210 air conditioner, but it could be a little bit more than that or a little bit less than that, depending on the actual conditions that it's operating in. So just be aware of that. So what is a cooling load? You'll hear us talk about the load of a house. Well, in the summer, the BTUs are more concentrated outside the house. And so they're going to come into the house. All right. They're going to conduct through the walls, through the windows, through the ceiling, through the floors, and they're going to make their way into the house, which is going to make the house warmer. Also, they come in the form of sunlight. All right. Radiant energy is a form of BTU transfer. So like a parked car sitting on in the parking lot, the sun's going to come in and it's going to get very warm inside. Those are BTUs coming in the form of sunlight. All right. Well, the cooling load of the house is how many BTUs per hour are coming into the house under certain conditions. And we use that number to size equipment. So we say, okay, there's this many BTUs coming in. So we need to make sure that we put an air conditioner on there that can remove at least that many BTUs. So it's what the house needs. All right. And it can be calculated. It can be calculated using software, and it can be calculated on a room by room basis if we want to design ducts and things like that. But it's the number of BTUs coming into the house that we can use to size the equipment. That's the calculated cooling load. All right. And then when we cool a house, when we apply mechanical cooling, we're removing those BTUs. All right. So an air conditioner that has a tested nominal cooling capacity of 20,000 BTUs per hour can remove 20,000 kitchen matches worth of heat from that house in 1 hour. All right. So we have cooling load is what the house needs. And then we have cooling or cooling capacity. Okay. And then the heating load is the opposite. It's the opposite direction of the heat flow. All right. So in the wintertime, all the BTUs are concentrated inside the house and they're escaping. They're conducting through the walls, through the floors, through the ceilings. They're escaping through leaks, air leaks in the house, and things like that. And so the heating load is the number of BTUs that are escaping that we have to replace if we want to maintain a comfortable temperature inside the house. Again, that number can be calculated. We can figure out how much heat is lost through the walls, how much heat is lost through the windows, how much heat is lost through the ceiling, and it's a number that we can determine, that we can estimate and calculate. And then we use that number to size the heat pump or the heater, the heating system of the house. And then heating itself is the process of adding BTUs to the house. It's replacing those BTUs. So if we say a heater has a capacity of 30,000 BTUs, that means it can put 30,000 kitchen matches worth of heat into the house in 1 hour. All right. So we have heat escaping and we have heat coming in. Okay. So to maintain a constant temperature, we need to maintain the density of BTUs inside the house. But if BTUs are leaving, we have to replace them. And if BTUs are coming in, we have to remove them at least the same rate that they're coming in or going out. So it's a balancing act. All right. So that's what we're after. Then capacity is the ability of the heating or cooling equipment to add or remove those BTUs. All right. So think of that as the supply. It's what the equipment gives us. It's the supply. And then the load is what the house needs. That's the demand. Okay. So we can calculate that demand, and then the manufacturer of the equipment can tell us what the supply is under design conditions, and we can match those together. All right. So good equipment sizing is the ability to match the equipment supply to the house's demand. And you don't want to be too big and you don't want to be too small. Okay. So it's a balancing act. You can be too small, but you can also be too big. So there's a nice range of the load that we pick the equipment that has to fit into this certain range. Okay. But here's the most important part of that discussion. If you don't calculate the load, you're totally guessing. All right. So it's super, super important to actually calculate what the house needs. Okay. So that's very important. We'll talk a little bit more about that in a minute. So when you undersize equipment, that means the capacity is substantially less than what the house needs. So it's not going to keep up. The demand of the house is greater than the supply, and so it's not going to keep up. On really, really cold days, it's not going to get to the temperature we want. On really, really hot days, it's not going to cool down to the temperature that we want. So that's undersized equipment. And that's what most people are afraid of. That's what they're worried about when they size equipment. But guess what? Oversizing can actually cause more problems. So we have to be very, very careful about not oversizing equipment as well. Oversizing is defined as when the capacity of equipment is substantially higher than what the house needs, than the load of the house. In other words, the supply is much, much greater than the demand. And this causes all kinds of other issues. Okay. And we'll talk a little bit about those too. So when we calculate the load of the house and when we calculate the design capacity of the equipment, we do it at certain conditions. All right. The design conditions. Okay. That's indoor temperatures and outdoor temperatures. All right. Those are code specified. You cannot mess around with those. You're supposed to use what the code tells you. And a lot of people don't understand where those numbers come from and what they mean. And so the tendency is to want to play around with those numbers, especially on the cooling side. If you look at the cooling design temperatures for a city, you're like, oh man, it gets much hotter than that. All right. But don't think of it that way. Don't think of if you say I'm going to do calculate my loads at a certain temperature, that oh, my air conditioner is only going to work when it's that temperature or less. That's not how it works. Okay. So follow the code when you do your load calculations, when you calculate your outdoor conditions, follow the loads. All right. And just be aware that these aren't the very worst temperatures expected in the summer or winter. All right. And the reason for that is we want our air conditioner to work on the mild days. Okay. We want our heat pump to work on the mild days and not just on the super extreme days. And if we designed it for the super extreme days, then it would be way oversized for the mild days and it wouldn't work as well. All right. So we have to choose, and we choose to make it work on the vast majority of days. It's by definition called the 99 percentile. All right. The temperatures that we choose for cooling is the 1 percentile. It's only greater than that temperature 1% of the time. All right. And so just be aware that those are code specified. All right. So the system needs to work at the milder conditions. If we design to the really bad conditions, the equipment is going to be oversized for most of the season. Oversizing will cause more comfort complaints than undersizing. I get asked to go out to a lot of problem houses where the homeowners just simply aren't comfortable and they can't figure out why. All right. The vast majority of homes where I've gone out and determined what was wrong with the house, it wasn't that the equipment was too small. It was that the equipment was too big and that the ducts were too small. All right. So oversized equipment with undersized ducts will cause most of the comfort complaints that I've dealt with. All right. So if you oversize the equipment, what happens is it only runs for a very short period of time. And we call that short cycling. And that causes all kinds of problems. And we're lucky we're in a dry climate compared to parts of the country like Florida and Mississippi and Louisiana. Short cycling causes humidity problems, right? So it's even worse than the problems we have here. Short cycling of equipment can reduce comfort. All right. It'll shorten the life of the equipment and it will increase energy use. So there's all kinds of problems caused by oversizing equipment. So again, you can be too small, but you have to realize that you can also be too big on your equipment. And the only way to know what's too small and what's too big is to actually calculate the load of the house, figure out what the house needs. And using rules of thumb like 500 square feet per ton and stuff like that, that is not a load calculation. That is a rule of thumb that has gotten people into a lot of trouble. All right. So it's very important that you do a good, precise load calculation on the house to determine the actual size of the equipment. Another thing that people do wrong is, especially if they're replacing a gas furnace and going to a heat pump is they'll use the capacity of the furnace to size the heat pump. That is guaranteed to oversize your heat pump. All right. So that's what the capacity of the furnace is what the furnace gives you. That's always much, much larger than it needs to be, just for a lot of reasons. Okay. So don't go by that. You got to do a load calculation on your house. And here's another very important point. When you do a load calculation on your house and then you look at the equipment, be aware that you can change the load of your house. You can improve your house. You can make your house better. And I always, always, always encourage people to take that should be your first option. Okay. Is to improve your house before you figure out what size equipment is going to go on there, because most houses, virtually all houses, can stand to be improved a certain extent. Okay. All right. So let's talk about super basic thermodynamics and the refrigeration cycle. Okay. So, as I mentioned, temperature is the density of BTUs in an object or a volume of fluid. So, let's say a house. All right. So the house on the right here has more BTUs inside of it. So it's going to be warmer. The temperature is going to be higher. And if you take away some of those BTUs, and you'll see on the left, it has fewer BTUs in that fixed volume. So the temperature is going to be lower. All right. Another really important concept to understand is that everything has some BTUs in it. The only place you can go where there's no BTUs is outer space. All right. So every single thing, even really, really cold air, even a block of ice has some BTUs in it. And you can extract those BTUs from that block of ice by putting something next to it that's actually colder than that block of ice, and the BTUs will go over there. Okay. So as I mentioned, when we heat something, that's adding BTUs. Okay. And when we cool something, we're removing BTUs. All right. And then there's something called the second law of thermodynamics, and that is that BTUs are naturally going to go from where there's more of them to where there's less of them. All right. From a higher temperature to a lower temperature. All right. Think of BTUs as being antisocial. They don't like each other. So they're going to want to go to where there's less of them. All right. So up here, we've got let's say there's a block of metal and it's very, very warm. There's a lot of BTUs in it. And then we've got another block of metal that's much cooler. It has less BTUs. And when we put those in contact, the BTUs are going to say, oh, look, let's go over there. There's fewer of them. And so they're all going to migrate to the block of metal that has fewer BTUs until it reaches a point of equilibrium where they're the same. And then they're going to stop. Okay. So the fact that BTUs naturally go from where there's more of them to where there's less of them is a very important concept. That's what causes BTUs to leave our house in the wintertime. There's more of them inside, and so they want to leave to go to where there's fewer of them. And then the same is true in the summertime. There's more of them outside, and they want to come inside where there's fewer of them. Okay. So that just does that naturally, but we can use that to our advantage. So you can also, if temperature is the density of BTUs, you can change the temperature of something not by changing the number of BTUs, but by changing the volume. All right. So on the left here, we've got a fixed volume of air or a gas that has a certain number of BTUs in it. We can make that gas warmer, not by adding BTUs, but by changing the volume, by making the volume smaller. We squish it down and the BTUs are closer together. They're more dense and the temperature goes up. And so now they want to leave because the temperature goes up. So if we take that volume of gas and we expand it to where it's 40 degrees, but it's inside a room that's 70 degrees, the 70-degree air has more BTUs. So they're naturally going to want to go inside this container because we've made it colder by expanding it. Okay. So it's like a BTU sponge. We've expanded the sponge, and now the BTUs are going to go inside because they just naturally go from a warmer to a cooler temperature. All right. Then we take that and we squish it becomes 100 degrees. Now the BTUs are going to leave. So now we're squeezing that sponge. So this gas that we expand and make it cold and then compress it and make it hot is literally a BTU sponge. We can expand it and absorb BTUs, and then we squish it out and the BTUs go out. All right. But it all depends on the relative temperature of the inside versus the outside. So the ability to mechanically change the temperature of something by changing its volume is what refrigeration and air conditioning is all about. All right. And that's basically what it does. Okay. So let's say we have a house that's at 70 degrees inside and 90 degrees outside. And BTUs are coming into the house at a certain rate. And if we can remove those at a certain rate, we can maintain that nice cool 70 degrees inside. All right. So what we do is we take our container and we go inside the house and we absorb those BTUs. And then we run outside and we squeeze out the BTUs. And then we run back inside and we absorb the BTUs. And we run outside and we go back and forth and back and forth and back and forth. And if we could do that and move the BTUs from the inside of the house to the outside house at the same rate that they're coming in, which we've calculated as a load calculation, and now we know how many BTUs we have to dump out of the house, we can maintain a comfortable temperature. Okay. So we have just mechanically moved BTUs in the opposite direction that they naturally want to go. All right. They want to come into the house, but we are mechanically removing them from the house. Guess what? In the wintertime, we can do the opposite. We can take BTUs from the cold outside air, absorb them and condense them and bring them inside the house. So this example that I gave you, this is air conditioning. The BTUs are outside, they want to come in and we're removing them. So that's what air conditioning is. Okay. But we can do the opposite. We can heat our house with the same principle by absorbing the BTUs outside, by making that gas colder than the outside air. The BTUs will absorb from that air. We bring it into the house and make that gas hotter than the inside air, and we've moved BTUs from the outside to the inside, the opposite direction that they naturally want to go. Okay. But obviously, having a container that we have to go in and out of the house with and absorb and compress and absorb and compress, that's not very practical. So, some very, very smart people a long time ago said, you know what, instead of individual containers like this, what if we just made it a pipe? And at one point in this pipe, they're being squeezed out. And at another point of this pipe, they're being absorbed and we make it a loop. Okay. Well, that's what this is. Okay. That's the refrigeration cycle. So inside the house, and this is air conditioning, inside the house, the gas is expanded. We call that the evaporator coil. It absorbs heat from the house and then it goes outside and then it goes through a compressor where the gas is squeezed and it gets very hot and it that hot gas then dumps the heat to the air. The air's colder than the gas, so that the BTUs go into the air, and we call that the condenser. So we have an evaporator where the heat is absorbed, and we have a condenser. Okay. Well, like I said, we can flip the direction and absorb heat from cold air and bring it inside the house. Okay. And that's what a heat pump does. Okay. So a heat pump um, squeezes the gas and dumps the heat to the inside of the house. And then that gas goes outside where it evaporates and gets very, very cold and absorbs heat even from very, very cold air. All right. Remember, everything has some BTUs in it. And the way we can extract those BTUs is by making something colder than whatever that thing was, the air. So if we can make that gas colder than the outside air, it will absorb heat. And then we bring that heat inside the house and squeeze it out of that gas. All right. So that's how a heat pump works. All right. So exactly what is a heat pump when we say a heat pump? All right. Well, it's an electric heater. It runs on electricity, which is good for a lot of reasons. Okay. But here's the interesting thing. When we talk about, or when someone says an electric heater, we typically think of an electric resistance heater, like a blow dryer or a plug-in heater or baseboard heaters or something like that, where you plug it into the wall and you turn it on and current runs through a wire and that wire gets really, really hot. That's electric resistance heating. Well, guess what? That is really efficient. It's essentially 100% efficient. It's like 99.8% efficient. Let's just call it 100% efficient. Okay. And if it's so efficient, then what's the problem? Well, the problem is electricity is expensive. Okay. So we actually need something better than 100% efficient. Well, it turns out that if you use this refrigeration cycle and instead of using that electricity to create heat, we use that electricity to move heat that already exists. So the air, even cold air, has BTUs in it. They're already there. They've already been created. All right. If we can just move them from one place to another, it's the same impact as creating them from scratch, which is what electric resistance does. It turns electricity directly into heat. But instead of doing it that way, we use that electricity and gather heat that's already there and move it inside. As it turns out, it takes about a third less energy, less electricity to move heat than it does to create heat. So an electric resistance heater will take 5 units of energy and turn that into 5 units of heat. That's pretty darn good, 100%. But we need better. We need better in order to compete with gas, which is cheaper than electricity for creating BTUs. So we need a better way to do it. So you can take, if you use a heat pump and the refrigeration cycle, you can take 2 units of electricity and move 5 or even 6 units of heat. Okay. So you can get the same amount of heat by consuming a lot less electricity. So that's why they're so efficient. Is they don't create heat, they steal heat. They cheat. They're stealing heat that's already there. They're just moving it, okay? And it takes a lot less electricity to do that. All right. So, what are some of the advantages of heat pump space heating? Um, well, one of them is people are worried about the technology, okay? But they've been around for a long time. It's a proven technology. Air conditioning has been around since the 1930s. Air conditioning is a heat pump just running in the opposite direction, okay? You're moving heat by compressing and expanding a gas from one place to another. We just call it air conditioning or cooling because we're moving the heat out of something, all right? But it's been around for a long time. The technology's there. Air conditioners move heat from the inside to the outside, where heat pumps move the heat from the outside to the inside. It's the exact same thing. It's just running in the opposite direction. All right. So heat pumps are basically air conditioners that run backwards in the wintertime. And a great marketing slogan that I heard one time from an HVAC contractor says, "Hey, you buy a heat pump from us, we'll give you a free air conditioner." It's the same piece of equipment. It just flips direction. Okay. All right. So a lot of questions they get asked. Well, how cold can it be for a heat pump to still work? All right. Well, if a heat pump is basically the refrigeration cycle, what's the coldest freezer you've ever seen? A box freezer, a chest freezer, the freezer in your house. What's the coldest freezer you've ever seen? Well, that is mechanically removing heat from the box. And if you can get it down to really 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 cold, that means it's able to extract heat from that really really cold box. All right, so you're basically moving heat from inside your freezer into your kitchen if that's where it's located. So if that box represents the outside of the house, it can move heat from that cold of a space and get it inside your house. Okay. So if it can pull heat out of a very cold freezer, it can pull heat out of very cold air outside as well. All right. So it is possible. Heat pumps have been successfully installed in some of the coldest regions of the world. I have friends in Minnesota and Pennsylvania where it gets really, really cold, and they have heat pumps on their house and they're working great. Okay. They're ideal for the Central Coast. Heat pumps, you could not pick a better place except maybe the San Francisco Bay Area. Really, really mild summers, mild winters. Heat pumps are perfect for that climate. Okay. Even in the coldest day of the winter, in your area, there's tons of BTUs in the air that you can extract. Okay. So if it'll work in Minnesota, it'll certainly work in San Luis Obispo and Ventura County and stuff like that. Okay. But you can have electric resistance heat as emergency heat. All right. If it gets extra, extra cold, some places, and the old way of doing it was to have electric resistance as supplementary heat for when the heat pump was having a little trouble keeping up. But guess what? In our climate, in the coastal climates of California, not necessary. You can size the heat pump to heat the house all by itself without putting any supplementary heat on there. You can, however, put electric resistance heat on there for emergency heat. In case something goes wrong with the heat pump equipment, you can put electric resistance heating on there for emergencies. Okay. But it is not necessary as supplemental heat to help the heat pump keep the house warm. Okay. All right. So, some big advantages of heat pumps, and one of my personal favorites, and one of the reasons I'm such a big proponent of heat pumps, is they're so much safer, so much safer. I came into the HVAC industry and profession right at the very end of all electric homes and when they started encouraging gas. And I designed a lot of HVAC systems that had gas, that were gas heaters, gas water heaters. And it always, always bothered me that we basically pipe an explosive gas into our homes and then we burn it where it turns into a poisonous gas, and then we try to get it safely out of our house. That just doesn't make sense to me. I've never been a big proponent of that. All right. So it's so much safer. There's no explosion danger of gas. There's no poisonous combustion gases like carbon monoxide. There's far fewer fire hazards. And if you want an illustration of just how important this is, a great quote from a building inspector told me, he goes, if you get a permit for anything, if you get a permit to replace a sink, replace a toilet, to do electrical stuff in your house, if you get a permit for anything and you have gas appliances in your house, the code's going to say, thou shalt put in a CO detector because it's that important. It's that important. And we have that many problems where we need to do it. Okay. So the potential for something to go very wrong with gas appliances is very, very likely. Okay. So we do have to be careful. So sorry to hound on that, but I've seen problems. I know people who've had issues. You just go on YouTube and Google exploding house and you'll see. Um, but there are other advantages. Okay. Um, they're simple. It's easier to install a heat pump than a gas furnace because you don't have to run gas to the house. You don't have to have flue vents to get the combustion products out of the house. You don't have to provide combustion air. All right. When you're burning gas, that flame needs oxygen to burn. So you have to somehow get fresh air to that flame, and that causes its own issues. Okay. So it's much simpler. Back, like I said, back when they started going from all electric homes to requiring the energy code started highly encouraging gas and basically discouraging electric. Now it's completely flipped. But back then, builders much preferred building all electric homes. It was cheaper and simpler to do. All right. Another advantage, overall, heat pumps require lower maintenance. Combustion appliances must be checked and adjusted regularly. Gas burner ports become clogged and dirty. Safety devices. If you open a gas furnace, if you take the front cover off a gas furnace, you're going to see tubes and wires and sensors and all this other stuff. 80% of that stuff are safety devices, all right, to prevent a really serious problem from happening. And those all need to be maintained. Those tubes break, they get holes in them, and it's how the furnace knows that the fan is running. And if it goes, oh, I can't tell if the fan is running, I'm not going to run. And it just shuts off. Okay. So it requires a lot of maintenance. All right. Um, gas condensates have to be drained out. All right. So there's a lot of different things. Now, one exception is that ductless mini splits do require frequent cleaning. A lot of people don't realize that the ductless cassettes on the wall, they have their own built-in filter, and that filter gets dirty. And if it starts getting moisture in it, it'll start growing stuff in there. So you want to be very careful about that. So ductless mini splits do require frequent cleaning, just so you know. Okay. All right. Another big advantage of heat pumps is they come in much smaller. As homes get more efficient, we need smaller pieces of equipment. And heat pumps the smallest you could buy was 1.5 tons. Well, there's a lot of ADUs being built. There's a lot of additions on homes and things like that. And mini splits come down to as small as 0.5 ton. All right. So they're more appropriately sized for the load of the house. You can also do zoning. You can put more small systems in a house and get better zoning and better thermal control. All right. So the ability to have smaller pieces of equipment is a big advantage. Okay. they're cleaner. There's no carbon emissions, obviously, depending on where you get your electricity, but this is improving every day, right? And if you've got rooftop solar or renewables on your home, it's a no-brainer. You basically own your own electrical company. Why are you paying the gas company for something that you can do with your own electricity? Okay. So big advantage there. They are very, very efficient. They move heat that already exists rather than creating it. So they're up to 300% plus efficient. Their super advanced technology has been incorporated into the equipment. Heat pumps have come a long way in the last few years. All right. And they're cost effective. Now, because they're so efficient, they can compete with gas in most parts of the country, actually. And it depends heavily, obviously, on the rates and time of use. Okay, but it is competing now, and that's great news. All right, partly because the California Energy Code was based on cost effectiveness, and it couldn't recommend electricity if it was more expensive to use. And now that heat pumps and heat pump water heaters particularly can compete with gas, now the code can say, yeah, let's start using heat pumps. Okay, and now the energy code also has another motive, which is decarbonization, is to stop using something that produces greenhouse gases and things like that as well. Okay. Also, just so you know, the little box here, heat pump efficiency is rated by a number called HSPF. That stands for heating seasonal performance factor. Higher is better for that. And then heat pumps, cooling efficiency, the air conditioning side is rated by something called SEER, seasonal energy efficiency and energy efficiency ratio, seasonal energy efficiency ratio. But now you're going to see a little two at the end of those because they've changed the testing protocols. So the old one was SEER, and now it's SEER 2 and EAR 2 and stuff like that. So just be aware that a heat pump has two efficiency ratings, one for heating, the HSPF, and one for cooling, which is the SEER and the EER. Okay. Oops. So some disadvantages of heat pumps. Um, they're more complicated. There's a lot more moving parts heat pump than there is in, say, a gas furnace or certainly electric resistance heating. Okay. So they do require more qualified technicians, just like cars have gotten way more complicated over the years. But technicians are being trained. All right. They're catching up. They're keeping up as best they can. Heat pumps have been around long enough now. They've been very popular that most technicians have good experience with fixing them. Okay. At the very, very beginning, that was a bit of a challenge to find a technician who could come out and fix your heat pump, but it's much better now than it was just a few years ago. All right. They do have more complicated controls because they don't heat the house as quickly as other forms of heat. You have to be careful not to expect them to do that. And so the controls, the thermostats, and the sensors that turn the heat pump on and off do require more intentional programming and things like that. Okay. If not set correctly, they can blow cold air during the defrost cycle, or they can kick into supplementary heat unnecessarily. So they can be a little bit more difficult to operate by homeowners, but a lot of heat pumps and thermostats and even heat pump water heaters are Wi-Fi based, and they have really great controls on your phone and things like that. So technology has kind of caught up and made it easier to control them. Um, One of the biggest ones that I run into a lot is heat pumps can be impacted by bad duct design. Okay. Primarily bad duct design, but also bad sizing. So bad design and installation, heat pumps are more susceptible. All right. A gas furnace is a dumb beast. There's flame and it's like, and it gives off heat. You just put it in your house and it heats your house. All right. But a heat pump, because it's using this refrigeration cycle, it's very susceptible to the conditions under which it's operating. One of those conditions is airflow. How much air is passing through that heat pump? So if you don't size your ducts correctly, it can have a big impact. So you have to be much more intentional and much more precise about how you size your equipment, which means load calcs. Okay, designers must be more careful with load calculations, and then sizing the equipment to match those load calculations, and then sizing the duct work to get good airflow. Okay, these have been required for years. Okay. Few contractors take the time to actually do a load calculation or a proper duct design. All right. And that's a big problem. It's time contractors start doing what they've been required to do by code for many, many years. But because heat pumps were just kind of dumb and they would work no matter how poorly you design them, they've kind of gotten away from doing good design work. Well, now we need to refocus on that because heat pumps are very susceptible to bad design. And so they need to spend more time designing the heat pumps. Okay. It's time contractors start doing what they're supposed to do. If a contractor tries to talk you out of a heat pump, right, find another contractor. I think most contractors have gotten away from that. When heat pumps first started making their resurgence in California, there was a lot of contractors saying, "No, no, no, you don't want a heat pump. Get a gas furnace. It's fine. You don't want a heat pump." There's all these problems with heat pumps. All those problems with heat pumps were caused by bad design. It's not a technology problem. It's a design problem. Okay. So some more
Russ,
disadvantage. Oh yeah.
before we move on, we did get a question
Mhm.
from Sarah asking whether the compressor requires any maintenance.
The compressor itself does not require much maintenance. If the system is properly installed, properly charged, and all the line sets have been checked for leaks by evacuation and all that. It'll run for a long, long time. I mean, look at it like an old refrigerator. I've got an old 7-Up machine out in my workshop that's from the 60s, that's been running on the same compressor since the 60s. So the compressors themselves are quite robust, and don't need a lot of maintenance as long as they're installed correctly. The worst thing, the most common problem is that when they were charged, they didn't evacuate all the what they call moisture basically, and things like that can cause problems. But if they're installed correctly, they'll last a long, long time without much maintenance. It's mainly the fan and the filters and things like that that require the maintenance. Yeah, yeah, good question. All right. So, did I get all the so grid reliability issues. So, we've in California, it's been somewhat notorious for the grid being unstable, and now we're just loading it up some more. All right. So, more demand on the grid increases the potential for failure. This is being addressed every single day. It is improving. All right. Making houses much more efficient so they work with smaller equipment will reduce demand on the grid. So that's another reason why I'm a huge proponent. So there's two sides of the equation. There's what the house gives you, and there's what the equipment gives you, the capacity of the equipment, and what the house needs. All right. Everyone is worried about and focuses on what the equipment gives you. Look at the house first. Say, is there something we can do to reduce the load of the house so that the equipment we put on there doesn't have to be so big? And there's always, always something you can do. All right. Unless your house is brand new and above code and super, super efficient, there's always something that can be done to that house to reduce the load. And when we do that, we don't put as much demand on the grid. All right. So just another reason to look at reducing load before sizing equipment. Um, they may require an upgraded electrical panel. If your house wasn't designed, the electrical system in your house wasn't designed for electric space heating and water heating, you may have to upgrade your panel. All right. But there's rebates specifically for doing this. And there's a lot of really cool technology out there too, options that help you avoid having to upgrade your panel. Okay. So definitely look into those things. Okay. So the good news is the advantages are wonderful. Safety, efficiency, simplicity, all those things. The advantages are wonderful. The disadvantages are avoidable and manageable, and they're improving over time. Okay. So things are coming around. Things are coming around. Things are getting better. People are getting better at fixing the problems. And so things are improving. And here's the thing. If you're weighing your options between a heat pump and a gas furnace, and you opt for a gas furnace, you're gonna have to live with that gas furnace for a long, long time. And I guarantee you, before that gas furnace is at the end of its life, you're gonna wish you would installed a heat pump. Okay, because things are improving that much. All right, but you have to make sure that you get a good contractor who does a good design on that house and does a good installation. Okay. All the problems that we've had with heat pumps, all the bad things you hear about heat pumps, like I said, those are design and installation problems. Those are not technology problems. It's not the heat pump's fault. All right. All right. Okay. So different types of heat pumps for space heating. Let's talk about the different types. So heat pumps come in a variety of configurations. Ducted split system heat pumps have been around for years. The first house that my wife and I bought back in 1990 after we got married um, had a heat pump in it. All right. It was a brand new house and it had a heat pump in it in 1990. So they've been around a long time and it worked great, by the way. We had no problems with it. Um, and so a split system is where you have an outdoor condenser, and then that's connected by refrigerant lines to an indoor air handler that has the evaporator coil in it. Okay. So they have an evaporator coil, which looks a lot like a regular furnace. It's just a box. It's got a fan in it. Okay. And so this unit over here looks a lot like a furnace. All right. But there's no gas being burned inside of it, and there's no poisonous gases coming off of it either. Okay, so you can put it anywhere inside the house and not have to worry about it. But those have been around for a long time. There's no gas lines, there's no flue vent. You don't have to give it combustion air so that it can breathe. All right, if you've ever seen a furnace that's in a closet, a gas furnace in a closet, and you'll notice that there's either an open pipe coming down from the attic to provide that air, or there's like an opening in the floor if you have a raised floor house. That's called combustion air openings. That's to give the flame oxygen to breathe. You don't need that with a heat pump. Okay. All right. So now the big thing, the cool thing, if you will, are mini splits. All right. And I always want to lead off with ducted mini splits because whenever people hear the word mini split, they automatically think of ductless mini splits. But it's very important to realize that there are also ducted mini splits, and I'm a big proponent of those. Okay. I ductless mini splits have their place, but they only give off a certain amount of heating and cooling to the room that they're located in. And if your heat pump is bigger than the load of that room, you need to get some of that capacity in the other parts of the house. And the best way to do that is with ducts. Okay. Depending on the house, of course. If you have a really, really super efficient house that's really well insulated, you can put your heat in one room and it will make its way to the other rooms. But not all houses are that efficient. All right. So you got to move the heat to other places. And yes, having ducts does introduce a certain amount of inefficiency if they leak and if they conduct. But you can improve that as well by bringing the ducts inside conditioned space and things like that. But it's very important to realize that there are ducted mini splits. Okay. So here's your outdoor unit. Here's a condenser. Okay. And then a lot of the indoor units are these little soffit mounted units. Excuse me. I'm at the tail end of a chest cold. Excuse me. Um, and they fit into a very small space, and the ducts can run around. They don't need a whole lot of room. Okay, so that's a ducted mini split. And then, of course, there's ductless mini splits. And a ductless mini split, you can have a wall-mounted cassette like this one down here. They make ceiling cassettes that fit flush in a ceiling, but they do protrude up into the attic, so you have to be aware of that. Um, but they work great. But again, remember, they heat and cool the space that they're in. The room that they're located in is where that heating and cooling is going. And the question is, how well is that going to distribute to other rooms? And one of the lazy ways that contractors tend to approach that is they say, oh, well, let's just put a head in every room. All right. I just was helping on a project where they were having all kinds of comfort problems. And the problem was that they put a head in every room, even a bathroom. They put a ductless mini split head in one of the bathrooms. And that means it was way, way, way oversized for that bathroom. And it was causing problems. Okay. So if you're using ductless mini splits, you want to make sure that you're not oversizing them too much. Okay. But another cool thing is you can have a condenser that runs multiple heads. You can have one condenser with multiple heads inside the house. Okay. That's pretty cool technology. It's very complicated. And it requires a certain level of competency on the installer's part to put that stuff in. But yeah, it works pretty well. Okay. But you do have to be careful with sizing. You can also you can mix and match these heads and have ductless and ducted heads on a single unit. Okay. A single outdoor unit. So very cool technology. But they do require very careful load calculations, duct design, and sizing of the equipment. Okay. All right. So typical heat pumps that we see every day, the most common heat pump, those are called air source heat pumps. They're getting their heat from the outside air. The condenser sits outside in the air. It's passing outside air through it, and it's extracting heat from that air. And then that heat is compressed by the gas and put inside the house. Okay. There's a lot of other kinds of heat pumps too. There's water source heat pumps that get heat from the water if you have a source of water. Okay. And there's geothermal heat pumps that get their heat from the ground. All right. Less common because they're more expensive and they require a certain site. You have to have certain things happening where the house is located in order to accommodate these things, but they're definitely possible. Geothermal, they can drill holes straight down, so you don't need as much room, but that can be very expensive. Or you can dig a trench and lay the pipes down in this trench and cover those pipes up. And those pipes are extracting heat from the ground instead of extracting them from the air. But you need more room. You got to dig these long trenches, so you need a much bigger yard, much bigger property to do that. But they are super, super efficient. And the nice thing about those is they're much less susceptible to the weather. All right. As the weather gets colder, air source heat pumps have to work harder. All right. Water source and geothermal heat pumps, because they're under the ground, they don't notice that the air temperature is changing. They're getting their heat from the ground, which stays at a very constant temperature. So they're very efficient. Okay, sizing heat pumps. Heat pumps provide both heating and cooling from the sensor. That one unit is providing you a certain amount of heating and cooling. So you have to be very intentional about how you size that. You've got a heating load and a cooling load that the house needs. And then you've got one piece of equipment that gives you a certain amount of heating, a certain amount of cooling. Do you size it for the heating load or do you size it for the cooling load? All right. And with a gas furnace, you can pick an air conditioner, size the air conditioner for the cooling load, and size the furnace for the heating load. And that's easy. All right. But you don't have that opportunity with a heat pump. So that is one of the disadvantages. Like I said, it requires more intentional design. So you have to know exactly what the house needs. And you can change what the house needs. You can improve the load of the house and change what the house needs. So you take that heat pump that provides you a certain amount of heating and a certain amount of cooling, and you have to prioritize what you're going to do. All right. Depending on the climate, the heat pump could be sized for fine just for heating, but then be undersized and vice versa. Okay. So you have to be very intentional. Be sure to use a qualified licensed contractor that understands ACCA Manual J, that's the industry standard for load calculations, ACCA Manual S, which is the industry standard for equipment selection, and ACCA Manual D, ACCA's Air Conditioning Contractors of America. Okay. These are required by code. These are all required by code. But you want to make sure that your installer understands these and uses them to size your equipment. Also be aware that there is a new Manual S that came out fairly recently that has a much greater focus on heat pumps. Okay. So good stuff there. Historically, most designers would size the heat pump for the cooling load. And then they would go look at the heating load, go, oh, it doesn't have enough heating for our heating load. Let's add electric resistance, supplementary heat to make up the difference. Okay. That's the old way to do it. Well, research, field studies, and improvements in heat pump technology show that heat pump systems, especially in California, especially on the coast, do not need supplementary resistance strips. In other words, you can size the heat pump to meet the heating load of the house without electric resistance heating. Okay. Heat pumps are working all over California. Tahoe and Truckee, there's heat pumps installed up there without supplementary heat strips, and they're working just fine. So if they can do that up there in the mountains, they can certainly do it down on the coast. Okay. All right. The general recommendation today is to size the heat pump to the larger of the heating or cooling load, Okay. And then you go look at the other load and you say, is it oversized? And if it's way oversized, you have to say, all right, what do I need to do? What do I need to drop it a size? Do I need to improve the house? Do I need to change the load? Okay. And so it does require more thought. And but there's ways to deal with that. Okay. Um, if part is oversized, and it's usually going to size the heating load, and then your air conditioning might be oversized on the air conditioning load, there are ways to negate the problems caused by oversizing. And one of the best ways to do that is to have good airflow. So the importance of good duct design really comes into play if the air conditioner side of your heat pump is bigger than it needs to be. All right. The way to prevent all those oversizing problems from happening is to have really good airflow. Okay. Also, now they have variable speed and two-stage heat pumps that can act like a smaller piece of equipment. So on the heating side, it acts like a 3 ton, but on the cooling side, it acts like a 2 ton. Okay, so it can change its capacity for to meet the needs. All right, so good stuff there, and but it does require some intentional design. Okay, all right. As long as your heat pump heating capacity is properly sized to handle the heat load without heat strips, the heat strips should never come on. So you should be okay there. Um, let's see. It looks like we got a question. How do you think the Title 24 Part 6 updated peak cooling will affect metric will affect sizing? Uh, it absolutely will. All right. And so, yeah, that is something that will have to come into play. It's just another complication that heat pumps require more intentional design. Because so what Sarah's asking is the new energy code has a disincentive for oversighting your air conditioner. Okay. And so when you're doing new construction, you certainly have to take that into consideration. But for changeouts and things like that, it does not come into play. All right, it's only for new construction. So that's where it'll have the biggest impact. And it's just like I said, it's just something you have to think about. You have to say, okay, well, if I'm not complying because I've got too much peak cooling use, I've got to do something to the house to reduce that so that I don't need such a big heat pump. And that's just good design. That's just making a house uh, efficient. Okay. So yes, it does. It is another level of complexity though. All right. Let's see. You can install electric resistance strips as emergency backup, but if you do, you want to make sure that it has good controls. Okay. If you install electric resistance as an emergency backup, the only time that electric strips should ever come on is when you turn the thermostat to emergency heat. Okay. And you can certainly do that. You can certainly do that. Okay. Another thing is people like, well, I've been trained, I've been brainwashed by utilities and everybody else to use setback and set up temperatures, okay, to save energy. Well, on heat pumps, you don't necessarily want to use setback and setup. Now, if you're the type of person who likes it cold in the house when you're sleeping at night, you can allow your heat pump to let the house cool off at night, but just be sure to don't expect it to heat the house back up very quickly. So when you recover from the colder night setback temperature, is have the recovery time set much sooner than you normally would. Give it time to gradually bring it back up to the warm temperature. Okay. One of the most common problems with new heat pump system is that the installers, the people installing this stuff, aren't familiar with the controls and the commissioning of the heat pumps. There was actually some language issues from some of the foreign manufactured heat pumps. Had some language issues with the instructions on how to install the heat pumps, and so we had some issues. I think most of those have been worked out, but the point is that the complexity of how you program this equipment and stuff like that has caused some issues. So you have to be patient with contractors, and I'm hoping that most of those have been resolved over the last few years. I know there's a lot of intercommunication between the trades and stuff like that, and making sure that they're properly sized. They've learned a lot from their past mistakes. Okay, but just be aware that if it's just not working correctly, call your installer and say, hey, get out here and make sure that it's programmed correctly. So there you go. Okay, so we got a few minutes left. Let's talk about heat pump for water heating. All right, for water heating. So same basic technology. All right. When we talk about electric water heating, we typically think electric resistance water heating, okay, which is running a current through a wire and that wire gets hot, okay, and that's 100% efficient. But we can use the same technology as a heat pump space heating with the expansion and compression of gas, and we can extract heat from the air by making the gas colder than the air, so it absorbs those BTUs, and then we bring that gas inside and we compress it hot, and then we put that heat into the water instead of putting it into the air inside the house. And so here's a photo of a heat pump water heater. All right. And one of the main things you'll notice about a heat pump water heater is it's got this big old thing on the top that's got a fan in it and it's moving air and it's blowing air. It's got some vents and stuff like that. And it sounds like a little dormitory refrigerator, a little compact refrigerator. You hear it running and stuff like that. Well, that's a heat pump. It's extracting heat from the air, it's compressing it and putting that heat into the water. Okay. So, um, same basic stuff, but we've covered a lot of this in the previous discussion, so we get to skip most of that. But there's two different kinds of water heaters. Okay. Am I missing a slide here? Nope. There's two kinds of water heaters. We have what we call instantaneous or tankless water heaters, and this is just generic water heaters in general. Okay. Water is heated as it comes in. It's instantly heated up to what we need. The advantages is you don't need a large tank to do that. There's no standby losses. These are ideal for vacation homes and stuff like that. But the disadvantage is it requires very high input. All right. You have to put a lot of gas into it or a lot of electricity in it because you're taking cold water and you're making it hot right away. All right. Heat pumps do not do this very well. So the other type of water heater is a storage water heater where you store a supply of hot water, and that allows the heat pump to heat it up over a period of time. All right. So you got a lot of water, 40, 50, 60, 70, 80 gallons of water, and it's kept hot all the time. Now, one of the disadvantages is you're constantly heating that water up, even if you're not using it. Okay. But the advantages is you can have multiple draws off of that. You can have multiple people taking showers at the same time. But the disadvantage is it can run out. You can run out of hot water, and then you have to wait a long time for that to recover. Okay. So just be aware that that's some of the issues. Nothing new here. All right. The problem, however, is that heat pumps heat the water more slowly than a gas or electric resistance. So if you're not careful and you let it run out of water, okay, hot water, it'll just take longer for it to recover. So generally speaking, what a lot of people do is if they're replacing a 50-gallon gas water heater, is they're going to replace it with a larger capacity heat pump water heater. So they have more storage capacity, so they don't have to worry quite as much. All right. But a lot of these water heaters are Wi-Fi based. You can control them from your phone. You can have special settings on them. If you know you're going to have family staying for vacation at Christmas time, you got people over taking showers, more showers than you normally take. You can adjust for that. You can turn the temperature up. You can have it run on electric resistance backup and stuff like that. So you just have to be a little more intentional, just like a space heat pump space heating, a little more intentional about it. Recirc system. Some people like a recirc system, which is basically a pump that pumps hot water through your house so that when you turn on a faucet somewhere, you don't have to wait for that hot water. Yeah, that's fine if that's what you like, but they do waste a lot of energy. So they can save water because you're not waiting for hot water to get there, but they can waste energy. So they can be continuous, which is really bad. You do not want a continuous water recirculating system. You want it on some kind of a timer. Okay. But the better ones, the newer ones are demand. You push a button and it starts the pump, and then you do your business and you come to wash your hands or whatever, and the hot water's there. Okay. So you're not continuously circulating water through the thing. So if you have one of these on your house, if you have a recirculating system in your house and you're thinking about installing a heat pump water heater, you want to really consider improving that recirc system and going to a demand system, and always, always, always insulate that recirc piping as much as you can because it is wasting a lot of heat. Okay. So definitely something to think about. So if you compare water heating fuel types, okay, you've got gas, you got electric resistance, you got electric heat pump. Okay. The installation costs, excuse me, for gas is very low. If you're replacing gas and you're putting in a gas water heater, it's very low. Electric resistance is very low if you're replacing electric resistance with electric resistance. Electric heat pump is high. All right, it's expensive. The units are more expensive. If you're going from a gas to electric, it can require some wiring and panel upgrades and things like that. So those things you have to think about. But the good news is there's lots of rebates out there. Okay, people are throwing money at these heat pumps. But let's look at the operating costs. Well, gas is low. Electric resistance is expensive. I lived in a house in college that had electric resistance heat. It was really expensive. That was the biggest part of our electric bill. But a heat pump is very low. And if you've got solar PV on your house, it's basically free, right? If so, definitely something to consider. Safety. Gas is bad. Gas has lots of problems, lots of potential issues with gas. Okay, a lot of carbon monoxide issues, venting issues, and things like that. Electric resistance safety is kind of medium because of the amount of electricity that they use. Heat pump, excuse me, excuse me. Heat pumps are good. They're very safe. Okay. On the environmental side, gas is bad. All right. It produces greenhouse gases and things like that. Electric resistance is medium because the amount of electricity that they use. Heat pumps are good. They win that battle. Gas has high performance, okay, because it heats the water very quickly. All right, electric resistance is kind of medium. Heat pumps heat the water very slowly, but it's manageable. It's manageable. You can, if you're intentional about how you use your hot water, how you control your heat pump water heater, you'll never notice that it's an issue. Okay, but you do have to be intentional about it. Okay, so heat pump water heaters. They use the refrigeration cycle that we talked about. They make the gas colder than the air, so they absorb heat from the air. They squeeze that gas to make it hotter than the water, and they put that heat into the water. Okay, very efficient. The warmer the air is, the easier it is for them to work. But the opposite is true too. The colder the air is, the harder they have to work to extract heat. So you do have to be careful about where you locate your heat pump water heater. Okay. We'll talk about that in just a second. So it is still much more efficient than electric resistance and cost competitive with natural gas. Okay. Um, they are super efficient. Okay. They move heat that already exists rather than creating it from scratch. And they're really, really advanced technology. You can get them where you can control it with your phone. They're Wi-Fi based and all that kind of stuff. Very cool technology. And in most markets, they're cost effective. They can compete with gas for costs for heating water. Okay. Some of the disadvantages is the equipment is more complicated. All right, because it has a refrigerant in it. Some plumbers may not be certified to work on refrigerants. Okay, so it requires a more qualified technician. The controls are more complicated. So when someone installs a heat pump water heater, they can't just walk away from it. They have to program it to make sure, and they have to talk to the homeowner and ask them how they plan to use it. How many people live in the house? How many people are going to take showers in the morning and stuff like that, and set the controls accordingly for that. All right. They can be a bit more difficult for homeowners to operate, but having the Wi-Fi controls makes it much easier. A lot of the user interface on some of the Wi-Fi controls are very, very simplistic and very informative. So really cool stuff going on there. Again, grid reliability issues. We talked about that. We are switching from gas to electric, so it's putting more demand on the electrical capacity of the grid. It may require upgraded panels, but again, there's ways to avoid that. Okay, and there's rebates to help cover those costs. Again, all the disadvantages of heat pump water heaters are avoidable, and they're improving over time. So may as well go for it. Like I said on gas space heating, if you buy a gas water heater now, you're gonna have to live with it for a long time, and there's a very good chance that you're gonna wish you'd gone to a heat pump. All right, so let's identify heat pump water heaters. What do they look like? How can you tell what they are? Um, they they're storage. They're big. They're storage. Okay, they come 40, 80 gallon sizes. Larger sizes even for multifamily that serve multiple units. Okay, um, they typically draw about 1.3 kWs, which is not a lot. Electroresistance elements typically draw between 4 and 5 kW. So if they do have to kick into electroresistance backup heat, they'll draw a lot more electricity, but it's there if you need it. Okay. All the major manufacturers um, manufacture heat pumps. Okay. So there's plenty to choose from out there now. They've come a long ways. There are two different kinds. The by far the most common kind of heat pump water heater is what we call an integrated. All right. That's where the tank and the heat pump unit itself are all on one unit. It sits on top of the unit. It's just one piece. They do make these split ones where the tank is in one location and the heat pump is somewhere else, and they're connected by some use refrigerant lines, some use hot water lines. Okay. Those are typically more expensive, but they're very, very efficient. You can put the tank anywhere you want to because it's just a storage tank, and then you can put the condenser in the ideal location for gathering heat. Okay. Some of the features, the heat pump is on top. There's some pretty fancy controls. You're typically going to see some sort of vents. That's where the air comes in and goes out. All right. Now keep this in mind. It's bringing in ambient air, whatever the air temperature is of the space that it's in, and it's dumping out cold air. Right. So you have to be very you have to realize that they're susceptible to being put in a wrong location. You cannot put these in a very enclosed closet, okay? But they also make them that are ducted. So you can put them in the closet and they will duct in air from another location and duct the cold air out to somewhere else, okay? Um, they do have a large storage tank. They do have an electrical connection, but they don't have a gas connection, okay? The split ones, there's no heat pump. The heat pump is a separate unit. Okay. And there'll be some sort of refrigerant lines or water lines connecting the condenser to the tank. Okay. So these are far less common, but they're quite efficient. They're quite expensive in most cases, but and more flexible as to where you can install them and things like that. But the integrated ones are by far more common. Okay. If you just look at electric resistance, if you look at electric resistance water heater, how do you know that it's not a heat pump water heater? Well, there's no little fan running with the little vents and fancy controls and stuff like that. It's basically going to be just a tank with these two bumps on it. All right. There's an upper bump and a lower bump. Now, let me go back. These have those same bumps because these have electric resistance backup inside of them, but it's got this big unit on the top, whereas an electric resistance water heater doesn't. Okay. It doesn't have the thing on the top, but it's got those two bumps on it. There's no gas and it's going to plug into the wall, or it's going to have it's going to have a wire, electrical power coming to it. Gas water heaters are pretty easy to tell. They've got a vent coming off the top, and they have a gas line, and they have some kind of a control with dials and things like that. There's going to be a vent down here and stuff like that. So it's pretty easy to tell gas water heaters from electric water heater. Okay. So some special considerations for heat pump water heaters. Um, they require electricity. So if you're going from a gas water heater to heat pump water heater, you have to evaluate the panel to make sure there's adequate panel capacity there, or there's other really cool technologies that allow you to avoid that. Okay, they may require an upgrade. Some of the new products require 240 volt, 15 amp. Okay, there's also some 115 volt units out there they're much smaller units, but they're good for really small apartments and ADUs and things like that. Okay. There are controls available for sharing circuits that give priority to one use over the other that allow you to avoid having to upgrade your panel. Okay. So there's some really cool technology out there that you should look into. Don't just assume that you got to add a panel or that you got to upgrade your panel. Talk to someone who really knows what they're talking about to see if you can avoid doing that. Ventilation. So they get their heat from the air. So you have to give it, you want to provide it as much warm air as possible. Okay. And it needs a certain volume of air. And the volume of air it needs is a little bit less than a one car garage. Okay. So 750 to 1,000 cubic feet. Okay. But if you put it in a closet, you can do that as long as that closet is ventilated from a space that has adequate volume. Okay. But like I said, there's also units that are ducted. So you can put the heat pump water heater in a very tight closet and then it brings in its own air from somewhere else, like the garage or the attic, and then it cools the air off and it blows that cold air somewhere else. All right. The preferred location for heat pump water heaters is the warmest spot you got. Okay. That can be inside the house, but garages are actually a pretty good location for a heat pump water heater. And it's an interesting thing that if you drive your car around, if you have a gasoline car and you drive that car around, that car gets really hot and you bring it inside, you park it inside the garage. Guess who's heat coming off that car? Your water heater. All right. So that's kind of a cool way to recycle that energy. Um, the byproduct of a heat pump water heater is cold air. So it's going to give off cold air. So be creative about that. Maybe you can help cool your garage on really hot days and things like that. So there's some interesting things that people are doing to take advantage of that. Recovery time, heat pump water heaters do take longer to recover. They heat the water more slowly. It takes longer to heat back up. Okay. So typically if you replace a water heater, you're going to replace it with a larger volume water heater. So you'll replace a 30-gallon gas with a 50-gallon heat pump, or a 50-gallon heat gas with an 85 or 80 75-gallon heat pump or something like that, so that you have more volume. All right. Most heat pump water heaters do have electric resistance elements for emergencies, okay, if you need it, but you want to make sure that your controls are set to avoid that as much as possible because they do use a lot more electricity when they run on electric resistance. Controls, models with connected functionality that allow mobile controls and status checking are very, very cool. I highly recommend that if you do invest in a heat pump water heater, that you get one that's Wi-Fi based so that you can control it from your phone. Set all controls as per manufacturer's instructions. Set temperature set point. A lot of them don't come with the ideal factory set point, so you have to be very intentional about that. Heat pump systems have several operating modes depending on the manufacturer. They go by different names. They'll have like heat pump mode, hybrid mode, boost mode, standard mode, vacation mode, things like that. I heard someone tell me that they saw one of the choices was efficiency mode, and so they thought that that would use the less electricity. Well, it turns out it did not, and so they had to, you have to read the instructions. Heat pump modes can be set for year-round use if the conditions are right, so that it will always run on heat pump. Okay. Avoid using other modes that may use energy needlessly. Okay. So that is it. With that, I will. No questions going on. Hopefully have a minute or two, but I'll turn it back over to Danica.
Awesome. Thank you so much, everyone, for attending this course and for to Russ as well. I'll make this super quick, so there may be more questions that can be addressed at the end. So, as always, if you have any energy code or calorie questions, we have a code coach program to answer those questions for you. Next slide, please. Thank you. And I actually just launched a poll, so please fill out that survey that I just launched and let us know your thoughts and what other improvements we should offer, and other courses that we should offer in the future. And if you have any questions with regards to receiving your education units, we have AIA and ICC available for this course. As mentioned in the beginning, we have the slides and recording, which will be sent to you in a couple of days on your inbox. And also, we don't have our and courses for Q1 on our website yet, but on the slide is a sneak peek of the courses that we'll be offering for January to March. And yeah, and with that, I'll pass it back to Russ in case there's any last questions. Um, yeah, thank you, everyone. Thank you. I will um, keep this open as people finish up the survey, and then I'll end it at around 10:59. Oh, I think everyone has participated in the survey. And with that, thank you so much, everyone. Thank you, Russ, again as well. And have a nice rest of your day.
Thanks, everyone.